colleagues, dear colleagues, let me introduce once more Professor Barnier, PP Shirshov Institute of Oceanography, and also Institute of Géosciences and Environment, Grenoble. 2 years ago, he presented a report about climatic modeling of eddies in the World Ocean and Atlantic Ocean. Now we shift to Somali Current and summer monsoon. So, please.
Thank you very much. So it's my pleasure to be here again, and thank you for inviting me to give a seminar. So this time it's going to be more an oceanography type seminar, which is we're going to really, rather than talking about models, really trying to investigate ocean processes, and we'll see how numerical models are used to investigate questions that we have in oceanography. So I have several collaborators. Part of this work was done by Kwame, who was a PhD student. So the outlines of my presentation, I will of course start to introduce the scientific question we want to address, and for that we'll start with an overview of the Indian Ocean circulation during the summer monsoon. Then I will describe how we set up models and the model strategy to address the questions above. And then we'll get into the main results. We're going to look at the various scenarios of eddy-eddy interaction in this region. We'll first look at how the model describes the Somali Current eddies, and then we'll discuss model results. I will have some conclusions to discuss. So let's start with the overview of the Indian Ocean. Of course, you all know that the seasonal cycle of the wind in the Indian Ocean. Now it's the winter monsoon, in the winter time, the summer time in the southern hemisphere. The Africa is heating while this part is cooling, so you have what you could call a sea breeze, coming from a very large scale sea breeze going from the cold to the warm, where you have ascendance. So that's what is driving. It's a thermal gradient that is driving the monsoon. And in July, of course, it's the other way around. The Asian continent is really overheating and with large ascendance, and so the airflow is going this way. So this reversal of the wind has a very strong impact on the ocean circulation. And so I'm describing, giving here a schematic of the ocean circulation. We're going to focus on that region in the Indian Ocean. This is during the summer monsoon. Doing so, because of the wind is blowing this way, the western boundary current, which is the Somali current, is flowing northward because of the sign of the wind stress curve over here. Of course, when the monsoon reverses, the current is flowing the other way around. So this seems, some kind of very logical, but the Indian Ocean is the only ocean in the world where the western boundary current is reversing sign during the season. The Gulf Stream, the Kuroshio, all the other big currents, because those are very big currents, they are named the Great Ocean Current, are very steady, usually in the flow, and this one, because of the monsoon, is reversing, which is really a drastic change in the circulation. So the circulation established comes out during the northwest monsoon, which is the summer monsoon. You have a Somali current here flowing north, with the first circulation loop, which is what we call the Southern Gyre. We must say that the ocean is crossing the equator, so this is a change important change in terms of vorticity balance for those currents. And there is a formation of the very large eddy here, which is named the Great Whirl, and we often observe during the summer, at the end of the summer, another eddy near the Socotra Island, which is named the Socotra eddy. So that circulation lasts, a few months. If you want to, so satellite images there are few observations in this region, especially in the last 20 years, because of pirates. research vessel down there to go along near the Somali coast since the last 20 years. So we have very few observations, we have few floats. So satellites is the main way of investigation. So if you look at a picture in June 2004, we see here the Great Whirl, you know, a large spot of hot water, and another large spot of hot water, which is the Southern Gyre, which I mentioned. You can still observe this one in July, and we can see that there are here cold waters. So between the two gyres, the two eddies, you have an upwelling of cold water coming up. And in August, then you cannot see anything. You know, temperature is rather homogeneous, so the whole area of the ocean has been some kind of surface homogenized, and we lost track of those two things. So we don't know what happened from July to August to those two patterns from satellite observations. Regarding salinity, this is a mean sea surface salinity. It's important because it will help to characterize those two circulation patterns. We see that the Gulf of Aden here in this region is rather salty, you know, and there are even at depth some salty water coming from the Red Sea and going there, while the Southern Gyre looks, the Southern Ocean, the southern part of the Indian Ocean looks much fresher. So we can expect salinity contrast that can help in our investigation to understand the processes. So the scenario that is described in papers from the 2000 is the following. In March, April, the wind is flowing this way. The Somali Current is going south. It meets the East African coastal current, and they just then move toward the east in the open ocean. And you get some kind of a residual here current. In May, the wind, there is basically very little wind. So the East Australian current begins.
I'm sorry. What does it mean slowly varying circulation? At which temporal scales?
That's why I'm going to it. After I describe that, I will explain this. Okay? And that's why I'm put this. So you will see in June, July, the wind start to pick up and blowing north. So the summer monsoon is beginning. So the Great Whirl begins to appear, and we have two what we call the cold wedges, which are cold waters upwelling, you know, coming up, and the Southern Gyre begin to form, and the Somali Current has crossed the equator. In September and August, the Somali Current is moving north, stop around this, and the Great Whirl is over there, and then the situation goes back. So we have, you know, this kind of situation cycle repeat itself, and described this way, you know, this vision conveys that the fact that when the wind starts, the Great Whirl builds up, the Southern Gyre increases here, then turns into a Somali Current that is fading or moving in this direction. The Great Whirl continues there, then circulation weakens when the wind weakens and reverses. So this is what I call slowly varying circulation. It varies slowly within the annual cycle, you know, in response to the wind forcing. When you look at altimetric observation, high frequency altimetric observation, so they give a slightly different picture, you know. So here, all those pictures, they saw the sea surface elevation anomaly in 1997, seen from the satellite, from July to August. So this is just 1 month. Before I showed you an annual cycle, you know, that's why I call slowly things varying. And here what you could see is that would be the Great Whirl, okay, and then you see that there is a large, significant cyclone, so anticyclonic circulation, cyclone attached to it, then another anticyclone over here, and you see these things are, you know, this one is increasing, rotating around, moving, and you see that this Great Whirl seems to increase, then this steady, you know, appears quite big, then we get a very large Great Whirl over there, and significant interaction between those two eddies. Then we see something coming from the south coming in, and you know, eventually those two patterns mix and then. So, and this happened in just 1 month. Okay, so this picture in the satellite view, they convey a quickly varying chaotic eddy-rich circulation patterns. So depending on which the way you look at it, you have two different views of the circulation over there.
Bernard, just to see, these are just different realizations of the same thing, right? Because it's different years, but approximately the same.
No, it's the same year. It's 90. This is satellite observation. It's the same year, and you go this way. August. No, okay. Let's see. Okay. No, you're right. You have 1 year, 1 year, 1 year, 1 year. But I'm sorry, okay, so you have, okay, in 1 month every year, and you see that from year to year it changes, and in 1 month the pattern can change quite rapidly. Okay, with your blood interaction. It's really, I forgot. I have another picture with, I show only 1 year, that's why I missed this one. Okay, so the question that we want to address then is you know, how can we put those two visions together? You know, how, you know, can we reconcile or put together the slowly varying circulation that responds to the monsoon and the quickly time varying chaotic eddying circulation seen in the satellites? Okay, and for that we decided to tackle those two questions by looking at the dynamical interaction between the two main patterns of the circulation, which are the Great Whirl and the Southern Gyre. And for this, we are going to use eddying model simulation, so model simulation that resolve eddies. Okay, so the three questions we would like to provide an answer is the following. What is the generating mechanism of the cyclones flanking the Great Whirl? We've seen the Great Whirl have cyclones on the side. What is the generating mechanism for those? What is the nature of the interaction between the Southern Gyre and the Great Whirl, which is not very well described in the observation at the moment. And then we see that the Socotra eddy appears sometime. What is the formation mechanism of the Socotra eddy? I think, Sasha, that reminds eventually you question that were addressed at Mazig at the time by Jim O'Brien and his group at the time you were visiting this lab. That was addressed with some kind of layered flows at this time. So the modeling approach, I'll start with the simulation strategy. So the simulation strategy is the following. We have a hierarchy of global model which I presented 2 years ago, which is the Draka hierarchy of model. So those are global models based on the same code, which is a ocean general circulation model plus a CIS model, but the CIS we don't really care in the Southern Ocean. And we have a model at resolution 2 degree, 1 degree, half degree, quarter degree, 1/12 degree. Okay? So the vertical grid varies from 46 to 300 levels. And the bottom topography is treated with, it's a level model, so fixed level, but the bottom topography, the last bottom cell is adjusted to the real depth, which is called the partial cell bottom topography. So what do we mean by eddy-resolving? So when we say, so what is it? So on this plot, on that scale here, you have kilometers in the log scale, you know, 1, 10, 100,000 kilometers. And we plotted on this line the zonal average of the internal radius of deformation, the first radius of deformation of the ocean, which is basically you could consider as being the mean eddy scale. So this means that eddies are generated with such a scale. So blue things are the resolution in kilometers of different model configuration. So the idea, to make things simple, is that if your model resolution is below that curve, it means you have a chance to resolve eddies. And if it's above, you have no chance to resolve it. That schematic is more complicated than that, but it's a schematic. So if we look at one chart, so the full line is a minimum value, and the black line is a maximum value of this radius of deformation. So in fact, we should say that if we should be below the minimum is safer to resolve the eddies. So you see that a quarter degree model is above that curve, you know, the mean one, you know, between 40 north and 40 south. And if you're looking at this one, the quarter degree is only would be only resolving between 20 north and 20 south, so in the tropical region. 112 degrees much is better, you know, it's really could resolve or permit eddies from 60 to 60, and 120 degrees even better, and then we can continue. So if we deal with this 20 north, 20 south band, which is the Indian Ocean, we can see that the 112 degree model is really in the range of resolving the eddies, and the quarter degree is marginally, it will permit eddies eventually not resolve them very accurately. So knowing this, what we've done is we used 5 different model simulations, global. They all have, so we constructed some kind of an ensemble, but it's not a proper ensemble in mathematical point of view, because it is to, you know, we have different versions of the code. Some models have different vertical levels. They don't use the same advection scheme. They don't use exactly always the time the same free slip, no slip code. But it is, you know, some kind of an ensemble where you vary sometimes a parameters, sometimes a forcing, something like this, okay? But all those runs are hindcast for, you know, 120 years, 30 years, 15 years. This is operational analysis, 7 years. So they do data assimilation of this one here. So data are assimilated, so they should be closer to observation. And this is another 37-year hindcast, okay? So resolution, one is only 1/4 degree, but all the other are 112 degree. One has a different advection scheme. We'll see that this is important for momentum. Okay, and the forcing fields are all derived from ECMWF reanalysis. This one is, those is just ERA interim. This one is derived from ERA 40. This one is operational real-time ECMWF forecast. And this one is based on ERA interim. But the forcing, when I say relative wind, it means that when you calculate the drag coefficient, the current velocity is included in the bulk formula. So you take into account the shear between the wind and the current. While when you use absolute wind, you consider that the ocean current is 0, so you don't take care of the on this one, we just take the current velocity divided by half. Okay, and some are partial slip boundary condition on the side, and some are free slip. Okay, so in total, we have 110 realization of the seasonal cycle. I'm not saying they are all independent, but we're going to do like they were independent. Okay. But if what happened 1 year in this region depends on what happened the year before, then they would not be completely independent. Okay, and so we use the 5-day mean output of all those experiments of the last 10 years of each simulation. Okay, and we focus on what is robust between those simulations, because we know that models are imperfect and they can be correct. So just a picture. This is a snapshot of the current speed in the 112 degree model. So in this region, we have, you know, we see a very large current in this region. So you see that the model is really resolving rather small scale eddies, and that the model is full of eddies everywhere. And of course, it resolves eddies much better in this region than it does in those regions. But in this region, there are some kind of shear instability which are still generated by the model. So, I'm sorry for the score, but this is a snapshot of the relative vorticity in one of the experiments. So what we see is when it's blue, it's anticyclonic, and when it's red, it's cyclonic. What we see is 2 large anticyclonic features. This is a Great Whirl. This is a Southern Gyre. We see some kind of a filament or shoot of positive vorticity, and we see a cyclone attached to this feature. So this looks a little bit like what we've seen in the satellite observation, with large anticyclone with a small flanked by a smaller cyclone. So I have a movie that is showing this, how does this goes, and I'll try to show it, but I'll take a chance.
Maybe click on there.
Okay, so it's going fast. Okay, there are several years. But you see that the Great Whirl is moving very fast and colliding very often with the Great Whirl. And of course, if you look at them, there are plenty of Rossby waves and everything. So we checked all the processes, you see this bunch of islands, you know, it's very interesting how they behave regarding vortices. There are plenty of interesting things in this. We checked the propagation of Kelvin wave, Rossby waves, and everything, and the model was pretty much accurate in this type of in this. So to validate the model a little bit more, we compare it to observation. So here I show the 1/4 degree model simulation, but we have the same result for the 1/12 degree. So we compare here the surface current from the maximum co-annular analysis. So this is an analysis from surface drifters. So they provided the observational reference. This is the observational reference for the current, and the sea surface elevation from activity. Here this is from the model. So basically, you know, you see the Southern Gyres, the South Equatorial Countercurrent, the Great Whirl, and the features are qualitatively and even quantitatively not bad represented. The 1/12 degree model, of course, has higher amplitude and gets closer to the observational reference. But I showed the 1/12 degree. But I showed the 1/4 degree model because in that region it did perform. We didn't expect the 1/4 degree model to be that one. That is September. So the other one was June, and this is September. So in September, the Great Whirl has grown pretty much, we see this, which is the Socotra eddy, and the South Equatorial Current. It looks a bit messy in the float. It's much more organized in the model. But basically, the model seems to reproduce okay these things. So now we get to, we have confidence in the model that we're reproducing the large-scale things in the seasonal cycle, and it generates two major features we want to look at, the Southern Gyre and the Great Whirl. So now, are we going to investigate the interaction between the two? So we